All right, let's keep birthing our star. Ooh, yes. It's not imagining a protostellar cloud like, ah!
It's like screaming.
Right.
But on the other side, it's
Yeah.
like, push.
And when it's done, like, I went through 30 million years of labor and you don't even call me. All right,
I'm
so
going to Star College, Mom.
I don't know. But you know, I'm so bright, that's why my mom calls me son.
So I have a quick question. So why does the Hayashi track start very luminous then?
Oh, it's because when the star is initially collapsing, it's powered by gravitational collapse. And if you run the numbers, the rate at which it is producing the gravitational power is much higher at the beginning than it is at the end when things have settled down and it's almost on a sequence. In fact, the protostar, an early stage protostar, is about the same luminosity as a red giant is. It's much more luminous than the star it becomes is, as a matter of fact. But we don't see them in the optical because they're shrouded in the dust, and so it's optically thick, but it infrared looking, you can see them. Good question. Okay, so, yeah, let's write what we just talked about there. So, point 3, round in the band. Point 3, now. Increasing central temperature causes decreasing core opacity, following Cramer's law. So this makes the core radiative. Energy escapes from it into the envelope more readily. It says luminosity rises, but it turns out the star is still shrinking, protostar is still shrinking. Only one way to make luminosity go up while you're shrinking, and that is for your surface temperature to go up. So that's why the star takes a turn moving diagonally upwards and to the left on the HR diagram. And turns out this is about the same time that nuclear reactions are beginning in earnest. For our one solar mass protostar. The first two steps of the PP1 chain, so in other words, up to the formation of helium-3, remember the last step is two helium-3s colliding with one another. First two steps of PP1 chain. And the CNO cycle up to the production of nitrogen 14. And calculations show that due to the strong CNO temperature dependence, the core becomes convective again. But not right away. In other words, it becomes radiative for a while, but then eventually switches over back to being convective again. After a time. How long is that time? I don't know. Some amount of time. And then we get to 0.5. When our protostar has been collapsing for about 25 million years for a one solar mass protostar. Out of the protest.
But there we go, under 0.5.
That's right, yes. 0.5. Epsilon nuclear becomes so large that the core expands, making epsilon gravity negative, i.e., when you're expanding, instead of losing gravitational potential energy, you're gaining it. So that has to be at the expense of the energy being generated by the nuclear reactions. It can't all go into radiation. In fact, it can be used up, expanding the core. You decided you're okay with it. You figured maybe you left in protest. Epsilon nuclear becomes so large that the core expands. Making epsilon gravity negative. Expanding the core means you're putting energy in to do work against gravity. So in fact, ironically enough, even though the nuclear energy generation rate has become larger, the luminosity actually drops because you're spending that energy expanding the core. Surface luminosity actually drops. And keeps decreasing as the star approaches the main sequence, value. Keeps decreasing towards the main sequence value. Specifically the ZAMS value. And they came up with zero element sequence just because we wanted to say ZAMS. Sam's. Sam's. Sam's at the Pro Store. So here we're dropping down towards the Sam's there.
What else? Sounds like a southern way to say it.
Yeah, Sam's. Shazam.
Got some lambs left.
When you've pretty much used up the carbon-12 in the core doing the CNO thing, there's got to be some left over because the sun is doing the CNO cycle now. So it says exhausted here in the notes, but it just must be very depleted. The full PP1 chain takes over and the star settles onto the main sequence. Birth announcements are now mailed out, shared on Facebook, and tweeted. ASTR's. Aww, isn't it cute? Any questions?
Did they send it out on Instagram too?
They can do that, yeah, they can do that. The stars are a little behind the times on this. They haven't really taken to that
It's kind of far away.
yet. Yeah,
Instagram.
yeah, the news just hasn't gotten there yet. You know? So, let me show you some tracks for various masses of protostars. And so that means sign in. Should have done that before. Oh. So first, here's a cute little picture from the Astronomy 111 textbook of the idea of this stage of protostellar collapse we've been talking about. This would all be post, that's not that's chapter 13, this chapter 12. So, yeah. These are on Blackboard, but I did not. So, this is just a cute little picture showing the idea of the protostar collapsing and collapsing and collapsing and getting hotter until, as you can see at the very second to last step there, ignition! And then it settles onto the 0H main sequence because pressure is not quite enough to balance gravity. And so it keeps shrinking and heating up, and eventually, in a nutshell, the core gets hot enough to ignite fusion, and a star is born, and all that kind of goodness. So let's look at some tracks for stars of different masses. Protostars of different masses. So here is the sun doing that business we talked about of over there where it goes right at the end there. Notice for a half solar mass star, a protostar, it doesn't do the rising luminosity period for a while and all that. It pretty much just drops all the way down. I mean, it takes a bit of a turn here, but it drops all the way down. And then notice for higher mass stars that they tend to leave the Hayashi track higher up and then move on an almost horizontal track as they collapse towards the main sequence. Furthermore, notice the time scales. The half solar mass star, 150 million years. Sun, 30 million years. 3 solar masses, 3 million years. 9 solar masses, 150,000 years. 15 solar masses, 60,000 years. You're hardly going to be able to finish your popcorn in only 60,000 years as you're watching these things. Yeah, anyway, okay. You're not insufficient.
No.
There's like, okay. So let's talk about the differences for the different masses there.
So how long would the higher mass that takes 60,000 years to form, how long would it stay on the main sequence?
What's its mass there? It's like 15 solar masses, a few million years.
Okay, so it's compared to when it started.
Yeah, so it's always true that the protostar stage is much shorter than the main sequence stage. The main sequence stage occupies about 90% of a star's life from birth to death, and that's pretty consistent for all masses, which is why most stars that we plot, if you plot an unbiased sample of stars, most of them are on the main sequence. Why? Because most stars are on the main sequence. Why? Because they spend most of their lives on the main sequence, and so if you catch a star at random, it's most likely to be in its main sequence stage of its life. It's true that the half solar mass stars, spends 150 million years collapsing, much longer than high mass stars even spend on the main sequence. But on the other hand, a high mass star spends much less time collapsing than it also spends on the main sequence. And the stars that take hundreds of millions of years to collapse spend many billions of years on the main sequence. So again, in the end, the protostar stage is only a short duration of the star's total life. Kind of like people too, if all goes well, spend 9 months gestating and a lot more than 9 months doing other things. So anyway, half solar mass star. C is never burned. It never does that partial CNO stuff because in the core because it never gets hot enough. And furthermore, temperatures stay cool enough and the opacity stays high enough that the star stays fully convective and thus on the Hayashi track all the way down to the main sequence. So it never has the core becoming hot enough to become transparent enough to start dumping more energy in the outer layers and having the luminosity go up as a result. So it never makes that turn upwards that a star like the sun's mass does. Of course, all of this is a result of computer modeling. This is not people writing down equations or whatever. I was writing down equations, but you have to solve with a computer. These results all come from detailed computer models. Temperatures stay cool enough. And protostar stays fully convective. And thus on the Hayashi track all the way to the main sequence. So they never make that turn, they just drop all the way down. ASTRs, the exciting ones. Central temperature quickly becomes high enough for carbon-12 burning and the conversion of hydrogen into helium-3. In other words, those first two steps of the proton-proton 1 chain. This causes them to leave the Hayashi track at higher luminosities and to follow nearly horizontal tracks, it turns out, in the HR diagram. Central T quickly becomes high enough for first two steps of PP1 chain and carbon-12 burning, causing star to leave Hayashi track at high luminosity. Protostar, causing protostar to leave Hayashi track at high luminosity and follow a nearly horizontal track to the main sequence. And that's chapter 12. Woo-hoo. Woo-hoo. So now I'm going to pause the video while I implore the viewer at home, or in their dorm room, or in their fraternity room, or wherever they may be, to watch the Low Mass Stars video on Crash Course Astronomy, just like we're about to do.